episode 19 now, I think, Underscope podcast. Today I'm joined by Dr. Babak Eslami. How you doing, Dr. Eslami? Welcome to the show.
Good. How are you, Aiden?
Doing fantastic. We were talking a little bit beforehand. Senior spring, it's just fun. I'm just enjoying life right now. I was talking to a bunch of MechE students. They were like, "Yeah, you got to bring on Dr. Eslami." So I was like, "All right." So then I sent you an email. Now here we are. So hope you're looking forward to it.
Absolutely. I'm happy to be here. Thank you very much for your
So it's
invitation.
funny is this is actually like the first time we've actually interacted. I think like one-on-one. Like I think I had you for my senior project like mid evaluation presentation, but other than that, this is the first time we're meeting. So
Yeah.
I'm excited for it in general. So everything I learned today is going to be new to me. So if you're the viewers out there, this is going to be new to me as well. So I'm looking forward to it. But we'll hop right into it. So Dr. Eslami, where are you from? Like, where'd you grow up, and like, what's some of your background here?
So yeah, I'm originally Iranian. We moved to. So my parents started thinking about immigrating to U.S. around 2000, 2002. What was the time they actually filed for immigration with the hope of providing better life and better education for their kids. And then through that process, because it was such a lengthy one, we were in line for 8 or 9 years. They decided that we moved to Dubai for my senior year in high school and then my university until this immigration goes through. So we moved to Dubai in 2003, 2004, where I finished my high school there. Then I joined American University in Sharjah, a very small city next to Dubai. And it's actually a branch of American University we have in US.
Wow.
And I did my freshman and sophomore year there. And at that time, our green card got approved. And we moved to US in 2008. And yeah, that's when I transferred all my courses and joined University of Maryland as a transfer student.
Wow. So I want to ask you this. How is like education? Is education like, do you talk to students here who go through like American high school and then like versus high school and like over in like the Middle East? Like, is there any like differences that you notice?
There are differences, and I'm not going to be comparing. So the education I received in Dubai is very similar to what we have in US here. However, it's pretty different in Iran. The education in Iran is heavily focused on theoretical aspects, and it's heavy math, regardless of what major you get into. So you probably have heard this, that the math that we cover in first or second year in university is usually covered in high school there. But on the other hand, what's missing, in my opinion, is that hands-on and actual application in there. I always make this joke that it can be quite often that you get an engineer graduated from a university that's heavy in math and physics that could design a drill for you but could not use a drill. And to me, these are the weaknesses and the strengths, and it's really hard to say what's good or what's bad. In my opinion, it should be a mix of both.
Right. It's not hard to say like which one's better necessarily, but it's interesting to talk about difference because when I spoke to Dr. Saha, because he's from Calcutta, and that's where like he also grew up there, and he said it's kind of the same thing. It's very like theoretical, like so much math based, and by his junior and senior year, he was taking like differential equations, linear algebra, like things math majors are doing over here.
Right. So to tell you a funny story, when I went to Dubai, so of course I used to go to English classes as a second English class to just learn the language. But it's one thing to learn the language, but it's another thing you walk into a math class that's being taught in English.
Wow.
So I could talk in English, but when they were talking about multiplication or division, when they were writing on board, I could know what they're talking about. But when they were speaking it, I had no idea what those terms were.
Wow.
Like Pythagorean theorem, we have completely a different word for it in Farsi, but I knew the rule. So it's funny. I used to be a very quiet student in those classes until we would get to the quiz or exam. And I never forget when we had our first quiz, my math teacher came back to me and said, and he was suspicious that I kind of cheated because I was that quiet a student at the corner of the class, never talking, and got full mark in the first quiz. He was like, where did you get this from? I'm like, I can't talk, but I can write math.
That is interesting. Let me ask you this: do you think you could teach like mechanical engineering courses in Farsi? Like, do you think you could?
No, that's a funny thing. So it's funny you asked that. I used to have a collaborator who was originally from Iran, and whenever we were talking, I was like, because all my education in mechanical has been in English. I just don't know the terms, and my brain just switches to English when I start talking about the technical terms.
Yeah, that's just so fascinating because, like, I mean, I heard learning a second language in general is hard enough, but then having to like learn like all these scientific mathematics in that language is like a whole nother beast. But that's really interesting. So when you were growing up, like when you were finishing high school in Dubai, did you know like you wanted to do some sort of engineering? Like what led you? So you came over to school in the United States. Like what kind of led you to that decision?
So the typical story you hear from mechanical engineers. I was good in math. I was good in physics.
Right.
And I had no idea which major to choose. And then we had these academic advisors in our high school. I went to him and I told him what I like. I actually did not like that much of hands-on stuff, to be honest, at that point in my high school. And when I talked to him, he said, mechanical engineering can be a good choice for you because it's diverse enough during the first couple of years for you to kind of get a sense of what you like and what you don't like about it. And then you can adjust accordingly. So that the main reason for me coming to mechanical was I was good in math, physics, and I did not know what I like or what I don't like. Yeah, and then it got to maybe third year when I joined University of Maryland. I got involved with a research group that was heavily hands-on. At that point, they were designing these automated assembly line for the Sherwin-Williams paintbrushes. So at that point, I was that typical engineer that could not use a drill, was very good with physics and math. And yeah, I started learning how to use the milling machine, how to use lathe, and I became in love with doing hands-on work. And since then, whatever I do, I make sure that there is experimentation involved, either in my research or and yeah, it was maybe my senior year in college where I turned into a hands-on guy.
Yeah. So what for people that, because I don't even know exactly what mechanical engineering is, I'm gonna be honest with you. So like what is it? Like what do you do?
So the mechanical engineering in general, I think from its classical definition is divided into two categories of solids and fluids. And regardless of what branch you go into, what mechanical engineering does is learning how the subsystems and components in individual systems talk to each other. So if I want to give an example in a fluid system, that would be, let's say, the HVAC. So you have, let's say, the air blower, then you have condensation, now you have piping, you have the vent coming out. How are these systems all connected to each other to bring the temperature of the room to the desired temperature? On the other hand, when you're in solids, let's say when I'm talking about screwdrivers, how is the gears designed? How are the electronics designed? So when I pull the trigger, I get the same torque that I want at the end of my tool. So learning about how these subsystems talk to each other to make a bigger system react in a way we want it to react is what mechanical engineering is about.
is it both? So is it both learning about the individual aspects of a part? So for example, like let's just take the HVAC example, right? Students, they learn what is condensation, like how does that actually work, like thermodynamically, on top of like how could you apply this, right? Is that like kind of what you're
Exactly, exactly. So I can mainly talk about the solid part of it because I have been always teaching the solid branch of mechanical. But for example, we have this material science course in sophomore year. We talk about uh, what are the properties of aluminum, what are the properties of plastics, and then in our measurement course, we start measuring properties of matter and learn how instrumentation plays a role in our measurements. And then in senior year, it's followed up by a course called design, where we actually say, all right, now you have, let's say, this individual gear made out of this material because of what you learned in sophomore year. Now, how should you design this gear in this system? So it's, as you said, it's both looking into individual components and then applying that theory to a bigger system.
That's really awesome. Do you personally, like in your classes, do you try and like give the theory and let your students like how could you apply this? Is that like what you kind of do, or
So what if I want to tell you my ultimate goal in teaching, they call it the teaching philosophy. Now it's sounding serious. Is how to teach my students how to learn on their own. And I, and what do I mean by that? It's one thing that I come and tell you, hey, 2 plus 2 is equal to 4. But it's another thing I teach you how summation works. And then you go ahead and use that technique for any numbers and be able to sum them up to get the value you want. That's my dream in teaching. So when it gets to mechanical engineering, what I try to do is, of course, I need to cover some theories. Those are, I tell my students, it's like when we start the course, it's like we have just bought an empty toolbox from Home Depot. Then these theories become to be our tools, the wrench, the screwdriver, and all of that. But what we care about is not having a fancy set of tools that we cannot use. That's as useless as it can get. What we care about is if we have a problem with our system, being able to open up our toolbox and say, oh, this wrench can be used to open up this bolt
solution,
or yeah, being the solution of that problem. So that's my main goal. So every time I give a theoretical background to something, I try to definitely link it to an application and kind of show them. To give you an example, and I try to not talk too much, is in my materials course.
It's all good. It really is.
In my materials course right now, typically material science course in sophomore year in mechanical tends to be very close to material science and chemistry. And no respect to chemistry and chemical engineering, but as a mechanical who is not as strong with chemistry and chemical, we try to stay away from it. So you guys learn FCC, BCC, crystal structures into depth, but for us, we care about them. But at the end of the day, what we care as a mechanical engineer is if I want to select an alloy for my tool, just know the properties.
Right.
The reasoning is important, and that comes from chemical engineering of why that alloy has those properties and how can we modify them. But what I try to do in that course is cover those theories and then tell them, all right, now we have this screwdriver. This semester, we are working with cordless Black & Decker and skilled screwdrivers.
Okay.
So students open them up, they dissect the whole tool, get to the individual components and see how they can come up with an improvement with the tool. So they go back and say, oh, we're going to replace this with this based on the theory we've learned and apply it to solve that issue.
That's really cool. I like your analogies. You ever think about becoming like a poet or something, or like a poet? But that's I like that. I like all your analogies. I think it's really awesome stuff. So kind of taking us back a little bit. So you transitioned from a theoretical kind of guy to end of senior year undergraduate to a hands-on. Then you went to go get your master's degree. So like, can you tell us a little bit about like what led you to that decision? Like, why get your master's when I just go right for the PhD?
Sure. Yeah, that's actually a good question. I never wanted to do PhD. So at that point that I became that hands-on guy, I was like, oh, I'm going to get my master's. And we had a very similar program like our 4+1 here. It used to be called BSMS program at Maryland. So in the same research group that they were doing Sherwin-Williams projects, a project came in that was fully funded. So it could pay for my master's and it could pay for my salary. And I could have stayed there 1 year longer to get my master's. I was like, oh, that it can't be any better deal.
Yeah.
And the project I worked there was designing an automated assembly line for these bolts or fasteners that they would change color as you would tighten them. So, you know, the main problem with our cars, let's say the bolts on our cars, the car wheels or bridges or different parts that we use bolts, is we don't know how tight they are. So we use torque meter, but there is always discrepancy between the torque you apply on the torque wrench and the bolts itself, how much torque it measures. These bolts, the way they are built is you tighten them until their color changes and you would know, oh, that's tight. And the good thing is if they get loosened, the color goes back. You're like, oh, that's loose. So it could save a ton of money in technician time to do the maintenance and all of that. So
I've never seen those bolts before. Are they like practical?
Yeah, so there is a company who was the sponsor with it, and they're called Smart Bolts. They are being manufactured in Gaithersburg, Maryland, and yeah, they are pretty. Of course, you do not want to use those on simple furniture and stuff because they're expensive. They're like $20 each. But for certain applications, they make sense. They will start saving money.
That's really cool.
So that project was the one I started thinking about, and then I got involved. I did my master's. At the end of my master's, I was talking to my, so I had an offer from that company to enter their company as an engineer. At the same time, I learned about these bolted joints in pressure vessels and boilers. So ASME has these codes. So if you walk down Kirkbride Hall, you look at the ceiling, there are all these pipings and all those bolts around those piping joints. So I wanted to design a theory where we would know exactly what torque we need to apply on those on those bolts to create that compression that we need to have on bolted joints. That was my idea for doing PhD. I talked to my advisor. He said, oh, it has great potential. We can definitely write proposals and get that. I applied for my PhD again at Maryland because I wanted to continue with the guy. Got the admission, got the offer letter. And I think it was like a month before we started, something happened on his end. He came to me and said, hey, Babak, I'm leaving the university. I'm not staying here. And at that point, I was already in the program. I hadn't applied anywhere else. I hadn't looked for jobs. So if that hadn't happened, I would probably not even go to PhD at all. I would probably find an industry job and go that way. So what I did was I started calling different faculty and tried to get their opinion of what would be the best move to do. One of the faculties I talked to, Santiago Solares, I talked to him, I told him I like experimental stuff, I like hands-on. He said, oh, I have a project that's funded by Department of Energy, but it's in nanotechnology. What if you join my lab and you give it a shot for 6 months? And then if you like it, you stay. If you don't like it, then during those 6 months, you are buying time for yourself to apply for jobs outside. So I started working for his lab, and my research field completely changed to nanotechnology. And now I'm here still doing that research in nanotechnology.
So was that then your dissertation then? Where that was this is at George Washington, right?
So yeah, so it's funny. We started at Maryland with him,
Mhm.
and during the third year of my PhD, he got an offer from George Washington University. So
Wow.
I moved with him.
Gotcha.
I moved with him, and this became my dissertation. So I have focused on developing imaging techniques for atomic force microscopy.
Yeah, you're gonna have to explain that one.
Yeah. So there is this. So when you think about microscope, the first thing we usually come up with, we think it's a camera, it's taking a picture for us, and we look at that image. But what this guy does, there's a little micro cantilever, very small. We're talking about 100 micrometer in length that we cannot see by eye.
Mhm.
And then we shine laser over the back of this cantilever, and then we measure the deflection through the reflection of the laser. So when this cantilever with its tip touches the surface, it starts bending, right? And when that bends, I measure the reflection through my photodiode, and I can get material properties over surfaces at micro and nano scale. So we started working in that with that microscope. So what we measure is a scan line by line of those reflections of that cantilever as I go over. So if there is a step and I'm measuring, this would bend, and then I would measure that reflection.
So based on the bend of the light, you can tell properties of this, or like
Yes, yes. So
what kind of
there,
properties? Like what?
so the vast, there are a very wide range of property. The main thing you can think of is electrostatic charges, for example.
Okay.
So when I bring this very close, it snaps in if it's electrostatically charged, right? So that is a reflection that I get in my signal.
Okay.
The other things that electrostatic charges, we can get viscoelastic property, we can get Young's modulus of matters. These days they're getting to magnetic properties, electrical conductivities, and all of that. But what my focus for PhD was, it was imaging. Very soft matters, polymers. The reason for that is when you bring something that is very soft, you can think of it as like a virus, biological virus. When we were poking it with this, the sample itself would give, and the cantilever would not deflect. So in my signal, I would not see anything.
So it would absorb it, like absorb it.
Right. It would not be able to measure what I wanted it to measure. So what we did, we tried to start an imaging method that can image very soft matters, and that became my PhD dissertation.
And what did you find out? Like what was the conclusion?
So it all became from my mechanical engineering vibrations, where how you can shake the cantilever rather than dragging it, but you shake it at certain frequency that would tap on this rather than dragging it. And that was the finding.
That's awesome. So then at the end of your PhD, did you go get industry? Or did you go like right into teaching, or what
So no, so my industrial experience was mainly with my master's project.
Yeah. Okay.
And I was in direct communication with the manager at the company, who was the sponsor of the project. But after my PhD, I went back to University of Maryland as a teaching faculty. And I taught there for 2 years, and I became the director of their nanometrology lab. They had a nanometrology lab where they had an atomic force microscope and a couple of other microscopes. So I kind of kept my research activities active in the background, because I knew in the back of my mind, I wanted to get into a tenure track position. And then fall 2018 was when I joined Widener University as an assistant professor.
And how did that position open up? Like what?
So yeah, I whoever is looking for a position in academic environment, that they probably have heard of higher ed jobs. I went to higher ed jobs. I had an alert system built in. I was looking for Pennsylvania, Delaware, Maryland. This position came up. What I really attracted my attention looking at the position here was the school size. So I would go to Maryland. Maryland has great system of engineering. The School of Engineering there is highly ranked. They have great resources, but the school is huge.
Yeah, it's gotta be like 40,000, 50,000, right?
Right.
Something
I
like
think
that.
if I'm not mistaken, that their mechanical engineering department is about 4,000 or 5,000 students. So I would walk into the vibrations course, which is a junior mechanical engineering course, and we have 130, 140 students, which I enjoyed at the very beginning. But down the road, I started realizing that I'm not getting the satisfaction that I'm after in teaching. So I would not know my students' names.
Right.
And the TAs would be grading them. I would have 5 TAs for the course. I would just walk in, spit out information, walk out as a robot. So and then when you get to a smaller schools, what is limited now is research. What was unique about Widener was they were actually after doing research in that position, and they had that a small class size that I was after. And that was the main reason that got me attracted to Widener.
Awesome. So what are some like your favorite, like some of your favorite moments here at Widener? Like, what do you like?
I'll never forget the first homecoming event at Widener. That was maybe the 4 or 5 weeks down the semester, and they were like, "Oh, there's this event that the students and faculty, their family, they get together, and we have a booth. You're welcome to join." So I told my wife, where we put our Widener gears on, and we walked. And it's kind of sad that we miss it these days because of all these virtual things. But whenever someone asks, "What's your favorite Widener event?" That's the first thing that comes to my mind. But of course, other than that, knowing the students, I never forget when I was here for interview. I was walking down the aisle with Professor Nicosia, and he was able to call his students by first name. And I was like, he's the chair of the department, and it's the largest department, and he knows his students by name. That tells a lot.
Right.
And so, yeah, the relationship with the students is unique. I've been to smaller schools. I'm not going to name them. I've been to smaller schools. I've taught there. The relationship is not what I have seen at Widener. And I can't wait to go back to normal situation where I have the students in my office, and hopefully a homecoming event where we can truly celebrate.
That's interesting. So when you got hired at Widener, that homecoming was like, that was your first ever homecoming ever?
At Widener.
Yeah. Okay. Gotcha. Yeah. I mean, homecoming. I mean, it's just a fun time because everyone comes back. You see like people from Pennsylvania Military College. It's just like an awesome experience.
Exactly. I mean, at Maryland, like larger schools, you don't see faculty.
Right.
You see students, alumni, but you never see a faculty. I was like, oh, faculty are invited to that.
The faculty here at Widener, like, they're just great. Like, everyone's just like, everyone knows each other. I'm grateful for that opportunity to like know my professors, and I think that's really one of the best things about Widener. What about your research here? So I know you said you kind of took your research from your PhD and you learned and you applied it here. So like, what are your current research interests in?
Right. So yeah, that atomic force microscopy research, basically developing imaging techniques with AFM, is my main mission, I would say. With that said, the bigger goal in AFM now is, why can't we just use it as not only a measuring technique or a tool, but a fabrication tool? For example, I come over a surface and I use that cantilever tip and write something on it at micro and nano scale. So during my PhD, I have been trying to image the very sensitive samples and trying to do this with very soft forces. But I'm thinking, what if now that I have such a control over it, what if I do it in the other direction and I intentionally apply aggressive forces to modify surface the way I want? With that said, there is this collaboration I have formed with Dr. Fuladi and other assistant professor at mechanical engineering department. We have a funding going on from the state of Pennsylvania in manufacturing and in 3D printing. So what we are doing there is helping the Ninja Tech company. They're in Mannheim, Pennsylvania. Those who are familiar with 3D printing, their filaments are very soft. When you 3D print them, you can squeeze it, you can turn it around, and it comes back to its original shape. Very soft and elastic polymers. The properties of those filaments change under different environmental conditions. So at very high humidities, low humidities, things are different. So what we are trying to do in that project is coming up with an optimum environment to 3D print with NinjaFlex, while I use macro scale material property characterizations like tensile testing, all of those cool stuff. And I use my AFM to image polymers because I know how to do that. It's now kind of using AFM in an actual industrial funded project.
So I mean, I'm gonna try and understand this because I know some viewers might be a little confused too. So one part of the project is trying to find the optimum conditions to 3D printing. Like, are you literally looking at like what's the humidity like? What temperature are we at? Like those kind of things. That's literally what you're looking at.
Exactly.
That, and you're trying to look at the properties of the 3D printing material itself, like.
Right. So when I'm printed at very low humidity, does the material get stronger or softer? And then is that because of micro scale polymer properties, like the long chain polymers are changing, or it's because of macro scale properties that are changing, like how filaments are bonding to each other in the 3D printer?
Okay, that makes sense. So like, have you found any like results yet, or are you still like?
Yeah, so we are very close to publish the very first paper.
Wow.
This is being published in one of the ASME peer-reviewed journals. We have 2 graduate students, 2 undergraduates that are working with us on that project.
Is this with Dylan Caputo and the lasers?
Yeah.
Okay.
So Dylan has been with this research group since summer 2019. He has done 2 Circa with me, and now he's helping us with
okay, because I remember talking to him about that, and he said something about lasers, and I was like, all right, cool. I don't know. All right, but now I get the full picture of it. Okay, that's really cool. Okay, it's coming full circle. That's awesome.
Yeah.
Well, Dr. Eslami, I just wanted to thank you so much for hopping onto the show today. It was really good talking to you. Really good getting to know you, first of all. Hopefully we're back in person. We'll meet up. We'll get it going. So
absolutely. Again, thank you very much for your invitation. Thanks for having me. Keep doing what you're doing, and best of luck with your last semester. Is it your last semester?
It is. Yeah, I'm in it here.
All right.
So thank you everyone who joined in. Yeah, thank you everyone who joined in. Make sure you like and subscribe if you like the content, and we'll see you next time on the next episode. All right, so everyone, see ya. Unless I stuck by you, you're a sunflower. I think you